the Laue's conditions form the basis of all diffraction. So, whenever Laue's conditions are satisfied, we get diffraction. So, you would have seen X-ray diffraction patterns of crystals, and you will see they come with various spots. We also discussed that in the diagram earlier on when we discussed the way in which we can compare microscopy, ordinary microscopy with X-ray diffraction. We showed some points which come out from the scattering experiment, and this whenever scattering experiments are done on crystalline objects, if it is a 3-dimensional crystal, we will get spots, and these spots therefore now represent the values of H1, H2, H3, that is where the spot will occur with respect to the reciprocal lattice, and therefore we will be able to not only find the coordinates of the reciprocal lattice point in terms of H1, H2, H3, which can be replaced later by HKL, the so called Miller indices. Now, this is where Laue completed this work, and he got the Nobel Prize in 1914, I think. Then the famous work of Bragg and Bragg, father and son Bragg, came up, and what is done is essentially we start from the Laue's condition. So, we start with these 3 conditions, okay, and then after starting from these 3 conditions, we divide the Laue conditions by H1, H2, H3 respectively, and subtract from each other. So, take the Laue condition, divide by H1, H2, H3, and you subtract. So, we get R dot A1 by H1 minus A2 by H2 is going to 0. So, whenever we have an expression like this, 2 vectors A dot B equals 0, that means A is perpendicular to B. This is vector analysis. So, therefore, we see that the reciprocal lattice vector H is perpendicular to A1 by H1 minus A2 by H2. The same logic we can apply to the other 2 sets, that is R dot A2 by H2 minus A3 by H3. So, reciprocal lattice will be perpendicular to A2 by H2 minus A3 by H3 and the third one as well. So, which essentially means that the vector R is perpendicular to the plane containing A1 by H1, A2 by H2 and A3 by H3. So, H1, H2, H3 are referred to as the Miller indices. We can replace H1, H2, H3 by HKL because most of the textbooks follow HKL. But this particular textbook which I have followed is that of Jack Dennett's, where this nomenclature has been used. So, the fact that R is perpendicular to A1 by H1, A2 by H2, A3 by H3 essentially tells us that if you have now the S naught by lambda coming in here, you remember the picture we drew, we have just reorganized that picture, I have rotated the picture such that I now represent a plane, and that plane is in terms of H1, H2, H3. So, this particular plane is characterized by the Miller indices H1, H2, H3 or HKL. So, this is a plane HKL. So, S naught by lambda comes here, and then it is scattered. You remember we wrote the angle 2 theta for the S naught by lambda to S by lambda direction. So, this angle is 2 theta, but since this plane is perpendicular to this vector R, you see that these 2 is divided into theta and theta. And therefore, we get the vector R to be perpendicular. Vector R is perpendicular to the plane containing A1 by H1, A2 by H2, A3 by H3, and that is this particular plane. So, vector R therefore, now is being perpendicular. The direction of S by lambda is indicated here, and if you look at this very carefully, essentially what we see is that this plane is like a mirror, and we are actually seeing the X-ray pattern because of the fact that the incoming radiation and the scattered radiation or the diffracted radiation are essentially a reflection from the plane. So, what Bragg and Bragg called this as a reflection. So, this can be approximated to a reflection. Of course, the radiation may go through into this crystal and so on, but from this particular plane in the crystal, we therefore have this S by lambda coming out as a reflection. So, the diffraction now becomes a reflection. So, whenever we now see a spot in a diffraction pattern, we identify the spot with the Miller index H1, H2, H3, and we say that is the reflection because of this particular plane which is at H1, H2, H3, the reflection of the incident ray is measured here. So, this is now coming as a point source from a point source, and this falls on the mirror. So, this again becomes a point, and that is how we get a collection of points depending upon the various orientations of the planes we can think of inside the crystal, which we have already discussed in the previous classes. We can get diffraction, the scattering or diffraction or reflection, all three are one and the same now. They come in specific directions. They obey the, of course, the laws of Laue, the conditions of Laue, and we get this one. So, if we now call the spacing between planes, this spacing, if we call that spacing as d of HKL, that is the distance of the plane between the two planes, d of HKL, then we can write this expression A1 dot H, because you can now see that if you go to the Laue's condition, we are essentially writing the Laue condition. A1 dot H is the Laue condition. This is A1 dot H. This will be equal to H1. Okay. So, A1 dot H, which is actually H1, A1 dot H is H1. Now, this is divided by H1 and modulus of H. So, this represents the distance between the planes. So, we can calculate d of H1, H2, H3 as A1 dot H1 dot H by the modulus of H. We know the modulus of H is 2 sin theta by lambda. A1 dot H is H, and therefore, we get an expression which is 1 divided by d of H1, H2, H3 is equal to 2 sin theta by lambda, or 2 d sin theta is equal to lambda. So, this is the so called Bragg's law, and this got the Nobel Prize in 1915. So, very interesting, it is just a mathematical jugglery, a little bit of reorganization of the equations which Laue derived. But why did it get also a Nobel Prize? It got a Nobel Prize because of its simplicity, number one, and secondly because of the fact that hereafter we can get to the distances associated with the planes directly by measuring the scattering angle and the wavelength. So, if we know the theta value and lambda, we know the value of d of HKL, and d of HKL is what we are interested in terms of the spacing between planes. Now, what you see here is 1 over d of HKL. So, the so called vector r has still got the dimensions of reciprocal length. So, the dimensions of reciprocal length associated with r will be associated with d of HKL also. So, the distance between the planes now is a real space quantity, d of HKL is therefore a real space quantity. This is something which is important and you should remember, because this is essentially telling that r is perpendicular to H1, H2, H3. Now, r is H, the reciprocal lattice vector, and both the Laue conditions and the Bragg equation are satisfied when the diffraction occurs. The other advantage is that now diffraction can be very easily understood as though it is a reflection, and the use of the Bragg equation will allow us for a direct determination of the reciprocal lattice quantities, which was not probably possible if we had used the 3 conditions of Laue. And that way practically this equation is the one which now tells us the entire geometry of the diffraction experiment which we have done. So, we not only get the information about the real space geometry, we also get information about the reciprocal space geometry, and the two geometries are related to each other. That means, if you have a well defined crystal with the symmetry which we have defined over the weeks, then that particular symmetry is reflected also into the reciprocal lattice. We will have to examine that more carefully as we go along, but essentially this is therefore the one of the key equations. In fact, along with this, the other 2 equations which we wrote earlier for the structure factor and the electron density, these 3 are the 3 key equations. Now, why do you ask that question? We ask that question because this now just gives us only the geometry associated with the crystal. It will tell us, in fact, based on this equation we can calculate the cell dimensions, and therefore the crystal system A, B, C, alpha, beta, gamma can be determined by using this expression. So, if we do an experiment using X-rays, the scattered X-rays will now follow the rules of Laue's conditions, and as a result they satisfy this equation. So, using this particular equation we get information about the d spacing. We also get the values of 1 over d and 1 over d we can call it as d star, a vector in reciprocal space. So, we can get solutions to A star, B star, C star, the values of the reciprocal lattice directly from this expression. Once we have the reciprocal lattice information, we can convert it into the direct space information. So, the geometry of the unit cell and its ABC alpha beta gamma values and its corresponding spacing of the planes inside the crystal, both will be we will be able to get using this equation. So, the entire geometry of scattering can be obtained. The other two equations which we discussed earlier on, scattering factor and the electron density, represent essentially the presence of the electron density inside this crystal. So, a combination of this to give us the geometry and a combination of the Fourier transform equation to give the electron density, in principle therefore should help in solving the structure. Finding out where the atoms are, what are the atoms is left to the other two equations. Finding out the environment in which that electron density is stuck because of obeying the Laue's conditions and following the Bragg's law, we will get the geometry that is associated with the crystal. So, therefore, the beginning of crystallography was done by these three gentlemen, Bragg and Max von Laue. So, both of them, in fact both groups, all three of them deserved therefore the Nobel Prize in those days, because this now forms the basis of structure determination. Fine. So, let us go further and see the more detail of this, how the diffraction is occurring, how the Bragg's law is coming into the picture. Bragg's law is now coming into the picture now as we see the intensities that come out from a diffraction experiment do not depend upon the lattice points, because the lattice point need not contain any atom. So, but in a unit cell, when you are putting these atoms, they form their own array. So, suppose you have one type of atom in the crystal, let us say the green type, they will form an array of their own satisfying this as the A direction, this is A direction and that is the B direction. So, because of the periodicity they will repeat itself in both these directions. So, this defines a lattice of atoms. Now, it is no longer a lattice of points, it is a lattice of atoms. Now, when we say it is a lattice of atoms, then the intensities should come out when the scattering occurs. Similarly, we can have another atom which defines a lattice of atoms, and these two can be put inside the crystal. So, inside the crystal we have now a diatomic molecule, let us say. So, this is one atom, that is the other atom. So, we have a diatomic molecule defining the crystal. So, that means now these crystal dimensions can be built in. So, this will be the A direction of the crystal, that will be the B direction of the crystal, and inside that we have the atoms located at x1, y1, z1, x2, y2, z2. So, the presence of x1, y1, z1 and x2, y2, z2 therefore is crucial with respect to the location inside the crystal. The location inside the crystal is with respect to the lattice points. So, the lattice points will be now associated with these black dots which we have shown here, the black dot here, the black dot here. So, this now defines our lattice. So, if these are the lattice that is defined, this is we are in the direct space, then when X-rays are shown, each and every atom will follow the Bragg's law. So, there are let us say 20 atoms associated with this one lattice point, each of them will follow the Bragg's law. So, the red atom will also scatter at theta, the blue atom will also scatter at theta, but what you measure is the reflection which is coming from the plane. Now, each and every plane is now a point represented in this two dimensional diagram, and therefore, this particular point is a plane which satisfies the Bragg's condition or the Laue's conditions. So, therefore, you get now from this point you have let us say the X-rays coming in this direction, they scatter from this point, go in that direction. So, this is what we measure. What we measure is therefore the black arrows, but remember the black arrows are coming originating from the positions of the atoms, and they contribute in parallel to the intensity that is coming out from the plane. So, when we measure the intensity from the plane, we have a collective measure of all these atoms scattering in that particular theta value. So, obviously, the intensity will be dependent upon where these atoms are located, and that is the main issue. We have to find out where these atoms are located. But the fact that we are getting it from the various planes which we can locate by Bragg's law, or for that matter the Laue's condition, will tell us that it is in principle possible to find where these atoms are, depending upon the intensity now. So, until now we depended upon the directions to get the geometry. The intensity associated with the diffraction spot will tell us where the atoms are. If, for example, if this red atom is associated with this lattice point, then the intensity will be totally dominated by the presence of that red atom. Okay, so, that is the logic which we will follow in getting into the details of how the scattering occurs. Here is a little example of the whole process. For example, if there is an incident beam, the Bragg equation is satisfied, the diffracted beam D can be recorded as a reflection of the incident beam I by a set of lattice points represented by HKL. So, these now represent the lattice points. Remember, when we say a HKL, all the parallel HKL planes are considered, and therefore, we show the HKL in brackets. Now, how each and every one of them contributes is very important, because we want to get contribution from every plane, even if they are parallel to each other. We will see how that behaves in a little while from now. So, whenever the angle of incidence satisfies the equation 2d sin theta is equal to lambda, we get this scattering. Okay. So, suppose we now consider the spacing between these two is d of HKL. Now, we found that 1 over d of HKL is related to 2 sin theta by lambda. How does that come about is shown in this construction. I have left it unexplained because I want you to get an explanation for that, and you already know this from your college days, how this Bragg's law comes up. I will just give you the idea about it. So, suppose you take this ray 1, it gets reflected from this plane and goes off, and here is a parallel plane which is placed at a distance of d of HKL. Okay. So, now we can see that this second ray is up to here. If we drop a prop point here which goes to P, so this drop a point here, you get perpendicular here, you go to Q. So, the extra length that is travelled by this second ray is Pb plus Bq. Now, therefore, this ray has travelled Pb plus Bq, but then the scattering occurs at an angle of theta. The spacing is d of HKL. Now, making use of the fact that the addition distance is Pb plus Bq, in principle you should be able to find out what is dHKL, because 1 over dHKL corresponds to 2 sin theta by lambda. Now, you have to therefore calculate the values of Pq and Bq in terms of the theta value. So, you see that this is also theta, that is also theta. So, you can calculate the length of Pb and length of Bq, that will be equal to the d of HKL. So, the additional distance that the ray travels is equal to d of HKL, because these two rays are parallel to each other. So, this is purely a geometrical phenomena, and therefore, we should be able to find out, and this satisfies the Bragg's condition. So, the Bragg condition is satisfied because of the fact that lambda is 2d sin theta lambda. And how do we get this? Pb plus Bq is what? You have to calculate Pb plus Bq. Pb plus Bq will give us 1 over d of HKL equals 2 sin theta by lambda, right, and therefore, that will give us the value of sin theta and this value of sin theta. Take the 2 sin theta values, and then you will get the value of 2 times dHKL. How does 2 dHKL come up? So, discuss this diagram in your mind. I want you to take it as a home lesson to find out that this diagram now illustrates the Bragg's law as 2d sin theta and lambda. The reason why I am not explaining it is because I want you to think about it. It is simple geometry, how Pb plus Bq add on, and what are the values of Pb and Bq, which essentially now gives us this parallel beam, and that will satisfy the Bragg condition. The other issue which I will discuss now and probably leave you after this is to essentially consider 3 different planes. This will also give you a hint of how to look at the previous diagram and arrive at 2d sin theta equals lambda. Now, the hint is the following. You see that you consider plane 210 alone. The plane 210 is parallel to several planes. So, if you consider 210 only, you will see that the incident ray is here and the diffracted ray goes like that. I have indicated plus and y as the directions. So, you will get an value of sin theta 210. So, since 2d sin theta is n lambda, you get a value of sin theta 210, d 210, this value in fact is equal to 2d 420, because you are now making 2 into 2 and 1 into 2. So, this distance by reciprocity will become half. So, if you double the HKL values by reciprocity, it becomes half. We have studied it already. So, you have 420, you also have 630, which is by 3 times. So, what you see here is the effect is to change the angle theta. The sin theta 210 is in fact this is, I have made a mistake here, I should correct it. So, you see that the angle here, which is the 2 theta angle or the sin theta, the theta angle will now ensure that sin 210 is half of 420 and 1/3 of 630. So, this means that if we consider the order of the reflection, if we consider let us say 210 as n equals 1, 420 as n equals 2 and 630 as n equals 3, then the value of n comes up here. So, we therefore have 2d sin theta is equal to n lambda. So, this is the general expression which you find in many textbooks. So, where does this n come from? N come from the fact that there are orders of reflections. So, n equals 1, n equals 2, n equals 3 and so on. When we do the X-ray diffraction experiment, the X-ray diffraction experiment will individually give the reflection idea. That means 2d sin theta will be equal to lambda for each one of them separately, because the angle theta is different from each other. So, this essentially now will tell us that the equation 2d sin theta equals n lambda is the one which is essentially covering the thing. So, let me expand this and show this is what he was telling. So, 210, 420 and 630, I am showing the diagram again, because I was not showing it in the slide mode. So, I will show it again, and to confirm that d 210 is 2 times d 210. So, 1/2 of sin 2 theta, 1/3 of sin 2. So, the angle you see here is becoming different from each other. So, when you do an X-ray diffraction experiment, you can get these individually the intensities, because of the values are being different. So, 2d sin theta is equal to lambda for all practical purposes, but when we deal with other issues like X-ray spectroscopy for example, then all the orders will appear together, and therefore, we have to use this formula 2d sin theta is n lambda. So, basically n can take different values, and that represents the so called order of the reflections. So, the order of the reflections come up as a consequence of the h and k doubling here and tripling here, which is resulting in the variations in the sin theta angles. So, this having seen this, now we will see what happens in the diffraction condition. So, this is a very important slide. For all practical purposes, I will use this slide to describe how the scattering experiment is happening and how we get to the diffraction conditions and how we get the reciprocal lattice points. So, what we do is we put a crystal here at the origin. So, the crystal is now having a dimension A in this direction, a dimension B in that direction. So, I am taking a 2-dimensional plane into account, and this 2-dimensional plane therefore will start from the origin 0 here. I will also say that the reciprocal lattice origin and the direct space origin coincide. Now, what happens is that the value of this is a 2-dimensional example. So, D12 is represented in this direction. That is because you see that the plane that is considered here, the second plane which we have drawn here, this is 0 0 0 plane. The plane which we have drawn here, which is 1 2 0. So, 1 along the A direction, half along the B direction. So, this makes it 1 2 0. So, this plane is now 1 2 0. If you consider this plane then it will be 2 1 0. It is a parallel plane. So, this is 1 2 0 and this is 2 1 0. So, if this is 1 2 0, this is 2 1 0, what would be the next plane? So, these are parallel planes anyway. So, if you have 1 2, then this plane will be 2 this plane will be 2 along this direction, and this in this direction it is 1. So, you see that the bread analogy which we discussed. So, you essentially have the planes going through this is the loaf of bread which is now having a orientation like this. So, we are cutting the bread piece along the 1 2 direction in this case, and in this case it is along the A equals 2 and B is equal to 1. Okay. And in this case it is A equals 3, B is equal to 2.5. So, the corresponding value will be the reciprocal value of that. So, we can read out the corresponding planes associated with this. So, what happens is this is D12. When we do the scattering experiment, the corresponding reciprocal point will appear at here position, and that represents D star 12. Notice that now this vector is in the reciprocal space, and since this vector is in the reciprocal space, we will therefore generate corresponding to each one of these parallel planes different points in the reciprocal space. So, suppose I take this as 1 2. Okay. So, this is now cutting at 1 and this is cutting at half the position. So, this then will be what? It will be 2 4. So, this will be 2 4, which is not shown here, but we can show the other example, which is essentially telling us that if you take this point 0 0 0 and go along this direction by 1 unit, okay, then you will have the 1 0 A star coming up here, and the B direction will be representing B star. It depends upon what is the angle of beta here, the value between A and B, which is gamma. So, the value of gamma now decides what should be the value between A star and B star. So, the value between A star and B star will be 180 minus that value of gamma. So, because this whole thing has to be 360 degrees. So, you have therefore the gamma value here, and 180 minus gamma will define the A star B star direction. Once we have the A star B star direction, you will have the planes will be identified by points. That is how you get the diffraction in terms of spots. The spots which you see from the diffraction experiments correspond to these reciprocal lattice points. So, once we have the dimensions of A, B and C, in principle we should be able to find out and index these spots. This process of finding out what are the values corresponding to H and K in this 2-dimensional plane is referred to as indexing. So, each and every point therefore is indexed with respect to the value of H and K. So, you see here that this particular point which is indexed is now corresponding to 1 2. Now, please notice that this 1 2 is the same as 1 2 up there. So, there is no change there. So, that means the value of H and K will still remain the same whether in the direct space or in the reciprocal space. It is essentially the way in which the reciprocal space develops with a value of which is proportional to 1 divided by the distance. So, in other words, it generates the reciprocal lattice point. So, planes in the direct space will generate points in the reciprocal space, and therefore, we call them as the reciprocal lattice points, and each and every reciprocal point therefore correspond to the plane in the crystal. So, the planes in the crystals will now therefore can be identified in the direct space by looking at the spots and indexing those spots. So, when I index this spot as 1 2, that means I am referring to the plane 1 2 in the real crystal. Okay. So, that way we can do these values, find all these values, and these values now represent the reciprocal space and the diffraction pattern. So, this is the direct space and the crystal structure. So, if there is an atom now sitting here, its contribution to this plane needs to be calculated in order to find the intensity of this spot. So, if there is an atom sitting here, for example, very close to 1 2, how are we going to calculate the intensity that can be associated with this spot, and that is something we will have to evaluate in the coming classes. So, at this time we have a few questions left unanswered which you have to answer. One is the answer to this diagram, and as a home exercise you can work it out how to arrive at the formula 2d HKL 2d sin theta equals lambda from this expression, from this diagram. So, you have to find out the perpendicular distance from this point to this, perpendicular distance from this point to this. So, the path difference is now Pb plus Bq. So, if it has travelled by that extra path, there is a corresponding phase difference. The phase difference will now introduce what? It will tell us at what theta angle the scattering is occurring, and therefore, the sin theta values can be calculated once we know the value of theta, and if we know the sin theta value, then we can possibly use 2 sin theta divided by lambda, which will give us the value of d of HKL. So, d of HKL is 1 over d of HKL, sorry 1 over d of HKL will be 2 sin theta divided by lambda, and that is how we calculate this particular value. So, but I want you to do it as a home exercise. The second one is an understanding of how 2d sin theta n lambda comes up. N is the order of the reflection. These T diagrams will help you in principle to identify how these diagrams are coming and what are the angles, interaxial angles between them, between I and D, and that will tell us the relationships, and therefore, we get the different values of n going from 1, 2, 3 and so on. So, essentially what we have, just a quick revision of what we did until now. We started with the scattering from a periodic array, and then we derived the expression using the Laue conditions, and having done the Laue conditions we derived the Bragg's law, and having done the Bragg's law we tried to understand in terms of the diffraction as a reflection from a plane, and then we identified that the scattering is coming from atoms and not from the planes, but then the atoms are now associated with the planes. We will do in the coming class how this association with the plane will generate the intensities, what is the contribution of each one of these atoms to this particular lattice point. And then we saw the 2d sin theta lambda and then 2d sin theta n lambda. And then we are now trying to get to an understanding of the reciprocal lattice points which come from the direct space lattice. This is something we will discuss again, and then see how we can arrive at the Bragg's law in reciprocal space, because we have the recording in reciprocal space. Whatever we get from a diffraction experiment gives us spots in reciprocal space, and so the geometry associated with this can be identified once we index the spots. And once we have this indexation done, then in principle we should therefore see how Bragg's law behaves in reciprocal space, and that is the material for our coming classes. Thank you.